This is the video of the distributed systems project, and the objective is to implement a system for remote file access, and the communication is carried out using the user datagram protocol, or UDP. On the left here, we can see the project structure. Include are all the header files that the linker will include. Next, we have the documents, which are the text files for writing. One is Billy, which is a short text file that can be successfully transmitted in one packet. Next is Cinderella, which is an extremely long text file that takes multiple packets to transmit. Next, we have the source files for both the client and the server. Common files are utility files that are used by both client and server. So on the left hand side, we can see the server, and the various flags are -RMI, which is the RMI scheme for at most once and at least once, -RLR, which is the receiver loss rate, -SP, which is the server port, and -SLR, which is the source port. Next, we have the client flags, which are -F for the freshness interval in milliseconds, -S, which is the server IP. We can notice that the server IP here is actually different from the client IP. The server IP ends with 148.168, while the client IP ends with 146.188. Next, we have the server port, which is the same as the server port on the left, the client port, and the debug flag, which prints out the logs. So now we'll go ahead and start up both programs. On the left, we have the server, and on the right, we have the client. So now let's start up both programs. So now let's try to read a file. As we haven't fetched the file previously, so our local cache is empty, so whatever number we key in will be invalid. So now let's try fetching a file from our server. Let's fetch Billy first. So going through the series of commands, first the client executes a get last modified time command, and because the file doesn't exist in its local cache, it will carry out a series of reads to download the file back to its local cache. For Billy, Billy is actually small enough so that one read is enough to get the entire contents of Billy across. Now let's check the contents of Billy. So let's start reading at index 3 for 100 bytes. So first, the client checks the file's last modified time against the freshness interval. Because the file's last modified time is more than 0.3 seconds, which is the freshness interval, the client will actually execute a get last modified time to the server. So now the server has returned the last modified time of Billy, and now the client knows that the last modified time of Billy from the server is the same as its own. So the file has not been modified. So next we look at the start position 3 and the text read, which is my name is Billy. So going back to the text file on the server, we can see that clearly he has omitted the first 3 bytes, which are high and the space, and has started reading from my name is Billy. Also take note that this is actually reading from its own internal cache. Now we have downloaded Billy. Let's exit to the main menu and try to download another file, Cinderella.txt. Whereas Billy only took a few packets to send across because it was a short file, you can see that Cinderella is sent across chunk by chunk. In fact, for each packet, we read Cinderella in until the full buffer size, and then we transmit the contents over across to the client. Now, let us try writing to a file. So before we start, the server copy is "Hi, my name is Billy," and on our local copy, it is also "Hi, my name is Billy." As mentioned before, the client first checks whether the file time is out of its freshness interval, and if it is, then it fetches from the server. So now let us demonstrate the write function. So let us write at offset 3, hello world. So as we can see from the command prompt just now, before we execute a write, this client also internally checks whether the last modified time is out of its own freshness interval, and if it is, it requests a copy. It checks the last modified time with the server to check if it has been modified, and if it has, it downloads and then writes true back to the server. So in this case, it has not been modified. So let us examine what happened. So here we can see that the server actually has a get last modified time command issued from the client. So now, next, after the get last modified time command, the client wishes to write to the server, and we can see that there's an execute write command here. Next, after that, it accepts the packet and then it sends a response back across to the client. So now let us examine the server copy. The server copy is now, hi, hello world, my name is Billy. And on our local copy, it is also, hi, hello world, my name is Billy. Now let us try out the append file function. As its name suggests, append file merely appends the given text at the end of the file. So let us append by Billy. Again, the same process takes place, and when we check the server copy, there is a by Billy behind. Similarly, our local copy will also have by Billy behind. Now we are going to test the clear content function. The clear content function removes the content in the file. So after we execute this function, the file in both our local cache and the server will both be empty. So now the server has hi, my name is Billy in billy.txt. When we go to the local file, it also has hi, my name is Billy. Now let's execute the clear content. And now local clear success, and then we clear on the server. So now the server side Billy is also empty. Now taking a look at the logs, first we see that there is a execute get last modified time command. So this, as before, is just to check whether the file has been modified. Next, there's a clear file command executed, and this clears the file on the server. Next, there is a get last modified time from the client to update its own internal time last modified of the file. Now let's go and read the file, and then we can see that there is very clearly nothing in the file. Now we'll be demonstrating the monitoring function for our distributed systems project. On the left is the server, and the server is on 172.21.148.168. On the top right is the client, and this is on 172.21.146.188. And on the bottom right is another client, but this client is on my local machine. Now, both of these clients have a copy of Billy in their local cache. First, let's examine the contents of Billy to make sure they're synchronized with the server. As we can see, both copies of Billy have their content as hi, my name is Billy, which is the same as the server's content. Now, the bottom right client will monitor the Billy file for a duration of 60 seconds. Now, the top right client will append by to the Billy file. Now, we can tell that there's a monitor success and there's packets being sent across from the server. From the local file, we can see that the server has
told the client that there are changes detected and for the client to re-download the file. Now we can see that the new content of the file is "Hi, my name is Billy, bye," which is what has been written over to the server. So now the monitoring is telling us that there is 43 seconds left. Now the monitoring duration has ended, and we can see that the server has also said that the local IP on port 2222 has its monitor duration expired. Now let us read the local file on the monitoring client. We can see that it is not fetching a new copy of the file because the server time and the client's last modified time is the same, which means to the client that the file has not been modified. Now we can see that the contents of the file is "Hi, my name is Billy, bye," which is the same as that of the server, and for the client that appended, when you attempt to read it, it is the same. So now our monitoring client has received the changes that the client above has written to the server. This is done through the server broadcasting all changes to all listening clients.
Now let us demonstrate function number 9, settings. It allows us to change the settings of the program. So first, let us change the server port number. Let us change it to 2221. And now let us try to fetch a file from a server. We can clearly see that there is no response and the client is persistently trying to get the file from the server. This is because the server is listening on port 2222. So all attempts by the client to fetch the file will result in failure because the server is blocking on port 2221. Now we are going to demonstrate the remove file in cache function. What this does is it removes the specified file from your local cache. So we clearly see that there are two files in our local cache, Billy and Cinderella. Let's remove Billy. Now file is removed. So when we go to read file, we can clearly see that only Cinderella is left. Now we are going to demonstrate the function clear cache. It functions similarly to number 6, but let us try first reading file. So now we see that we have two files in our cache. So now we have two files in our cache, and after we execute the clear cache command, we have cleared our cache successfully. So upon us trying to read the file, there's very clearly no files left in the cache. Now we'll be demonstrating idempotent operation. In this case, our idempotent operation is to clear content in the file. So first, let us fetch billy.txt. Now we will try to read Billy, and we can clearly see that the contents of Billy are "Hi, my name is Billy," same as the server. Now we will clear the content of the file. Next, we can see that the server file has already been cleared. Now we will try to clear the file again. So idempotent operations their results do not change no matter how many times they're executed. Over here, we can clearly see that we've executed clear file function twice, but the contents of Billy remain the same if no matter how many times we cleared our content. So just to be clear, we have executed a clear file content here, and once again above, we have executed another clear file content. So after two clear file contents, the result is still the same. The contents of Billy is still empty. Now we'll be demonstrating a non-idempotent operation. So first, we'll read our local Billy file, and we can see that our local Billy file has nothing. So next, we will append file,
and we'll say, "Hi, my name is," to Billy. So now the text that we wanted to append is appended to the server-sided copy. Next, we'll append again. So now the state of the file is, "Hi, my name is." Next, we'll append Billy to the server. And we can clearly observe that the contents of the file have changed after we executed append a second time. In fact, if we were to append again, we can see that this exclamation mark would be appended to the text file. So it is clear that the result of append file is not constant. Its result depends on whether there is a previous append file executed. So hence, the result of append file will always change upon its execution. Thus, it is a non-idempotent operation. Here we'll be demonstrating the at least once remote method invocation semantics, and we have an extremely low receiving loss rate while an extremely high sending loss rate. This is because we want the server to receive successfully but send unsuccessfully. This is because if we take a look at the console app, we can see that the timeout is at 1000 milliseconds or 1 second. So after 1 second, the client will time out and will resend the same request. So now let us try. And now taking a look at Billy, we can see that his text file is also, "Hi, my name is Billy." And if we look at the local copy on the client side, we can see that the client copy is also, "Hi, my name is Billy." Now let us demonstrate at least once method invocation semantics. And we'll append by behind. Now, whenever the server receives but fails to send, as we can see here, simulating failed sending, the client will timeout and resend the same request across to the server. In this case, because the client has timed out again and it sends a request across to the server, it has resulted in 2 identical requests being sent across to the server. So now the server copy is actually, "Hi, my name is Billy, bye." But if we check the client copy, you can actually see that the client copy is only, "Hi, my name is Billy, bye." Now we'll be demonstrating at most once remote method invocation semantics. So first, let us read the contents of our Billy file. And we can see that the contents of Billy is, "Hi, my name is Billy." And over on the server side, the same contents are in the file. Now let us demonstrate what happens when we do an append file with at most once method semantics. So let us append by. And we can see that the client actually times out and sends the request multiple times across to the server. But over on the server side, we can see that only 1 by has been appended behind. The key reason for this is because of 2 key data structures on the server side. Firstly, we have a request map, which stores every unique request in a key value pair. The key is firstly the client IP and the client port, and next we have the value, which is the hash of the request string. Next, we have the response map, which stores the response sent into a key value pair. So here we can see that the key is the client IP port and the map value is a unique hash. So when the server encounters a new request, it checks to see if this request key is already inside its map.
if it internal hash map. If it is, it checks if there's already a response. So if there is already a response, it will retrieve the response and it will send the response across to the client. So this system is fault tolerant and the result of the exchange will be correct. So this is how we maintain at most once method semantics. Now we have come to the end of our video demonstration for the distributed systems project. Through this project, we have learned about what it takes to design a distributed system that is tolerant towards drop packets and other faults. So first, we have also learned about the at most once method invocation, how to store our requests and responses so that they are invoked at most once. We have also learned about at least once remote method invocation. We have also learned what it takes to marshal and unmarshal data structures across the network and into the client or the server respectively, and learned about the importance of marshalling due to the difference between network ordering and the host byte ordering. Next, we also learn about client timeouts so that the client will repeatedly retry its request until it gets a response back from the server. All in all, this project was highly enriching and taught us about distributed systems. Thank you.